Someone like you, you had like 3 year-old on the ground. Well, I probably just went around those guys. Oh, I think it's still not going straight. You got those like rack on the back of it? Yeah. Not really.
I'll be back in a minute. Oh no, it's having trouble creating the notebook. Every time I get back, yeah, probably. Man, okay. Yeah. I was kind of burnt out. Yeah. Someone else stands up and finally work. Like half your brain still works in life. Well, like I worked at home before, like you use Apple, you can get the you guys have to do it on like I'm not good at like trying to keep doing what I'm talking about. That didn't have to learn, but this some of this terminology is a little different now. I have like, it's like, I had a good, like, way to do before. I don't think things like a letter pot, you don't have like a linear and a top. You think of one thing and like four other things on. Have you ever had any of those? I haven't. How was it? How were you? So they went about it first. And then I was at the one where like somebody cheated. Yeah, and then we had to write out our not yeah. But hey, he's in that class with us. Good. This is his third time taking it too. No way. Really? So video. Well, it might be not as real. I'm not speaking right now because I was like, if we were talking about that, we were going to
Oh my God. I think we've reached the point where technology is now a complete hindrance to daily function. All right. Well, while it's doing that, let's go over. Okay. Okay. So is this where we are? So in here, this computer is really, really slow. So I guess I should talk really, really slow. So if you hit the mastering assignments button and then you wait 15 minutes. Okay. Come on, come on, come on. Go. Okay, there we go. I've had a couple of questions about this intro to mastering engineering. Go ahead and do that. It came with the system, and it's supposed to, give you some guidance about entering units and all that sort of stuff. Plus, I think it's 3 points, kind of 3 points that just get added for doing it. And if you don't get something right, don't worry about it, because I go back and I push what's it called? Accept everything button on that one. So just go through that one. But let's go to the one which is the one that I put together for here. Okay, so okay. So first of all, was there any one of those you wanted to look at yet? I mean, it looks like 4 people have done that. One person's done that. Nobody's got past that yet. So probably isn't a lot of questions yet. Let's see. I don't know which. I'll go to the highest number backwards. How about that? So technically, we got through viscosity. We talked for a minute about bulk. the bulk modulus. It's not very useful for us. So essentially, we're done with chapter 1. So I think I might, I guess I could start on chapter 2, but I want to kind of fill in a little bit. And if this doesn't come in up in the next, 20 or 30 minutes, I guess we'll. Okay, loading. I don't know what the issue is there. This is an interesting one. I like it. I like the picture there. Is this the correct view though? Standard view. That's what I want to see. God, that may take 20 minutes to. Let's see what the standard view looks like. Should be the statement on the left, something under there, and then the places to enter the thing on the right. Oh, geez. Okay. Okay, that's what I generally see. Okay. So it says a rain cloud is approximately a volume of 6.5 cubic miles. And an average height top to bottom of 350 feet. 1 mile is equal to that. If a cylindrical 6-foot diameter collects 2 inches of water if the 6-foot diameter collects 2 inches of water after the rainfall, estimate the total weight of the rain that fell from the cloud. So how would you do that? There's a couple of ways you could think of it. Okay, so let me go in and first I got 350 feet and I got 6.5 miles cubic miles. What I want to do is get the air projection. In other words, if you're laying on your back on the ground, you look up at the cloud, you don't see this dimension, but you see an area. And then that area would be a ratio to the area that you see down here. So in essence, is this the right thing? Okay, I tried to get that to work. I guess that's probably good enough. So if you got 6, if you got 6.5 miles cubed, and you get 5,280 feet for 1 mile. I got that backwards, don't I? I'm going to get rid of the mile. Mile, 5,280 feet. But I need to be cubing it, so I cube it. So I get 6.5, 5280 feet cubed. So that's how many cubic feet is in that cloud. But if you look at it, here's your cloud from the top or bottom. So this has a certain area. So the area times 50 feet. Let me look back. Oops. So it says the thing is tight, top to bottom is 350 feet. Right here. So that area times 350 feet is equal to that number. So the area projected, or the area that you would see if you laid on your back next to that water bucket and just looked up and saw this big cloud, you would see this many cubic feet. I mean, this many square feet. You would see 6.5, 5280 cubed, and then you'd see that divided by 350, because 350 feet, that sure isn't very much. So that's how many square feet you get. Now, I think, let's see, I've been cracking on modern technology because but I've been also using it. I'm allowed to crack on it too. Okay, so I don't know what the heck. That is a really weird thing, but okay, so let's see. Let me see if I can write this out. 2, 6, 5, 6, 7, 4, 8, 101. I think they're digits. I could care less about the digits. 2 billion square feet. Okay, so that's how many feet squared that the person sees there. Now, the bucket, is it 6 foot in diameter or 6 foot radius? 6 foot in diameter. And what did it do? It collects 2 inches of water. Okay, hang on. This thing has an area. Like 6 foot. The bucket collects. That's an awful drawing. But it collects 2 inches of water, or 2/12 of a foot, or 1/6 of a foot. So the projected area there is pi, or pi r squared, but that's 3 squared. That's the area of the thing, times 2/12 is equal to the volume total of the water that's in there. So I have no idea what that is, but I'm going to let that math thing. So that's why I've been cracking on people. I'm using this photo math. Because it just solved it. 4.7. So it is 4.71 cubic feet. The funny thing is, if you make the assumption the rain is homogeneous, then this is the projected area of your bucket, which is, you know what? I'm so lazy. I'm going to do that. That's funny. What's that? 28.27. So the ratio of this, okay, that is the area. Okay, so assuming the rain fell and it was a homogeneous amount falling, then that's the area you got. The ratio is okay, area of the cloud, the area of the bucket is going to be 26, 5, 6, 7, 48, 101 over 28.27. I don't know if that 27 matters. So let's see what that is. And that's assuming that it gets all the numbers right. Okay, that's equal to 9.4 e to the 7. So in other words, whatever, if it's homogeneous, there's a certain amount of water that falls in there. And if it's homogeneous, then essentially 2 inches, if that bucket fills up with 2 inches of water, then the whole area underneath this cloud, so if you think about it, the whole area underneath this cloud should be filled, you know, here's the area, but it's like some sort of thing with 2 inches of water all around it. So if you want to, you can make the distinction that you take that number of feet squared, you multiply it times 2/12, and that gives you a volume, and then you multiply times the gamma of the water. So in other words, if somebody says, I mean, this is probably not true, but if somebody says, well, you know, Russellville got 2 inches of water, of rain today. Yeah, that's a lot of rain. How much rain is that? Well, if it's 2 inches over the size of this table, you know, it's not as much as if it's 2 inches over the entire acreage of the, say, the campus. So the campus size is probably, I actually have no idea. What do you think? Maybe, well, we got these fields over here too. I have no idea. Maybe a couple, 200 acres? I don't know. So what you would do is multiply that depth times the whole area. So what I would do is take the area of the entire thing, area of the cloud, times 2/12 of a foot, and that's the volume of water that fell if rain is homogeneous, and that's a lot. Okay, so I'm so tired, but let's just 748,101 times 2 divided by 12. That would be the volume in cubic feet. Okay, let's figure that one out. Hopefully it won't think that's squared. It does think that's squared. Like that. Okay. It doesn't think that's squared. 4,279,135,0. That's cubic feet. Because we went. Let's see. Did I do anything wrong there? 5,280 feet, cubic feet. So it's a cubic foot, cubic mile. Basically, this number comes out. Look down here. That's the volume of water. If I want to know 62.4, now, I don't remember what the question was. The question. Okay, estimate the total weight of the rain that fell from the cloud. Okay. This you have to make some assumptions. One, the whole thing is homogeneous, things like that. Besides that, I don't know. I have to make that assumption, otherwise you can't solve it. So this would be pounds per cubic foot, and that would be let's see if this would calculate that with the unit stuck on there. I wonder if it will. I never tried to do this with the units on there. Couldn't recognize the problem. Okay. So 4,427,9,135,0 times 62.4 equals to, let's try that without the units. You think that it would maybe adjust the units or something. Okay, 2.7630180240. Wait, okay. 2.7630180240. So I don't know how you're supposed to enter this in this system. It's 3 significant digits. 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. Or are you supposed to do 2.76 e to the 10th? Which one are you supposed to do? I don't know. Let me just try. This should be pounds, but I don't know. Let's just say LB. I don't know. Let's 2.76 e to the 10th? What would happen if I did that? The value should be entered to a single number or in scientific notation. Is that not scientific notation? Oh, maybe. Okay. Okay, so here. There may be a trick to this. Okay, I think there was 7. 1, 2, 3, 4, 5, 6, 7. Oops, wait a minute. 1, 2, 3, 4, 5, 6, 7. However, I think you can enter the others as well. I don't think it takes off credit. What the heck? Let me just enter that. 301-80240. 301-80240. What the heck? I wonder if it counts off if I don't put in 3 significant figures. Okay, it doesn't care. 2.84. No, well, somewhere I got 2.76. We got 2.84. I don't know. I have no idea. Oh, your answer was either rounded differently or uses a different number of significant figures that required for this part. Here we learn how to estimate the weight of rain that fell from the approximate dimensions of its diameter. You know what? I think he may have solved this completely different. He may have determined the volume of the water and ratioed it. And I just assumed it was 2 inches covering the whole ground, which would be the same, which should be the same answer. So I started doing it the other way, and I started thinking, hey, wait a minute. If it's 2 inches, you're assuming that it covers the whole ground. You know what? How many gallons is that? Just out of curiosity. Because that's 6 cubic miles, but not a lot of area there. Let's see. Gallons per cubic feet. Let's try to find that. Well, let's just go on. Man, how many is it? 8 gallons is a cubic? No, it's maybe like 6 or something. I don't know. Anyway, it's something like that. Or maybe it's 4.48 gallons is a cubic foot. Anyway, it's a lot of gallons. That's why you have civil engineers to make sure that the drainage on your highway goes okay. Otherwise, people need to have boats instead of cars. So that's a typical problem there. I don't know. Let's look at this one. Yeah. Nobody's got to that one yet. Okay. Hello. I guess I need to build in like a 2-minute to 5-minute time for it to be able to find its way through the problem there. Oh, and then it says wait, or just wait it out. Okay, it came up so far with that. Okay. Oh, there it is. That's weird. So this is what's funny is it'll give you gives me results from everyone who's taken the course, like nationwide. So it gives me a chance to see how you're doing versus everybody else. And actually, it's been kind of interesting. We do about the same as the rest of the places do, so there's not much difference. Okay, it says viscosity of the 30 weight SAE 1030 oil is that, and the specific gravity is that. Then it says determine the kinematic viscosity. So that is a simple thing of definitions. So you got you got the dynamic viscosity, and then what's called the kinematic viscosity. And there's really only one difference there, and that is this. And I cannot ever make the symbol right with my hands, so it's kind of something like that. If you go look at it, it's like okay, let me just look on the web and just see what they say for the symbol. It's just, did I type that right? Maybe I didn't. Okay. Oh, I put okay. It says kinematic, absolute dynamic versus the kinematic. I had, it's an engineering toolbox. Here, Wikipedia. So see what his units, what his symbol looks like. So, okay. Oh, interesting. So we're cursed with one simple thing, and that is physicists got involved with fluid mechanics. And when they did, they created their own units, and our symbols are slightly different. So if you get down here, this should be interesting to see. That's the standard form. That's this, that the mu right there. If you get down here, how does he use? Here's the kinematic form. I don't know why I have so much trouble writing that symbol, but it bugs me, and I just can't get it quite right. So maybe it's a good time to practice. So here, I guess it's a straight down. Okay, here we go. So he goes straight down and then over like that. Is that it? No, it's straight down and over like this. But it looks so weird when I do it. So that's all it is. It's the dynamic viscosity over the density. There's nothing more to it than that. So then the key in this problem is, what is the density? Well, he didn't give you the density in the problem. He gave you the specific gravity. So he's telling you that related to water, that this is 0.92 times lighter. So in other words, some books use SG. Apparently this one just uses S. Okay, let me go back to the thing. So he just uses the S. Oh, I think it's for oil. So he says it's 0.92. But the definition of that is, okay, it could be the density over the density of the oil over the density of water at 4 degrees C. Or it could also be the specific weight over water at 4 degrees C. And the reason we picked 4 degrees C is because if you look at the plot of the density, I'm accentuating it here. But 4 degrees C, this is the density as a function of temperature. And at 4 degrees C, it reaches a top or a maximum. So anything less than that on either side goes down. So they picked that because it's a standard, Well, it turns out, okay, for SI, this is kind of the definition, kilograms per meter to the cube, is the density of water at 4 degrees C. 4 degrees C. So that's kind of the definition. That, the SI units were born out of, after Newton came around, and they were born out of scientific knowledge about things. In other words, they used water a lot. They used things like that. So that's how they defined density. And that's how they defined actually the kilogram mass as well. So a lot of stuff rotates around water, so to speak. So this means if you look at this equation, you've got these terms, in which if you want to know the density of oil, it's 0.92, which has no units. This has no units. And it's times 1,000 kilograms per cubic meter, or it's 920 kilograms per meter to the cube. And that's it. Now, the key is how do you find this? Okay. Let me try this again. I guess did I draw it that way before? Yeah. So all you're doing here is taking the number he gave you and dividing by 920 kilograms per cubic meter. So you're dividing the dynamic viscosity by that. And I do not remember what the number he gave us was. 0.1 Newton second meter squared. Hang on. Is that right? 0.1. 0.1 Newton meter second squared. Did I write that down right? Newton second meter squared. Newton second meter squared. Over 920 kilogram per meter to the cube. Big problem. Your biggest problem is when you find a force and a mass together. You cannot have that. So the question is, which one do you keep? And you may find that you don't need to keep either. So let's go ahead through the process of extracting this. And so how do we extract it? F is equal to MA, or a Newton is equal to a kilogram meter second squared. So if I'll take this in and put up in here, my units become now, I'll take this top one first. I'll say kilogram meter second squared, and then I'll take these two, which will be second meter squared over kilogram meter to the cube. So what I'll try to do is reduce the obvious first. And so on top, if I'm seeing this correct, I may make a mistake here. MS over M to the 3. So if you come down here, I believe you're going to get, okay, so, oh man. So I have a, that doesn't seem like it's the right units to me. Let me reduce them this way. Okay, so I'm going to break down the top. And I'm going to say a Newton second, a meter to the -2. Then I'm going to take a kilogram to the -1, and a meter to the third. So what I did is I took all of this from all of this. Now I'm going to put my Newton in here. I'm going to say kilogram meter second to the -2 times second times meter to the -2 kilogram to the -1 and meter to the cube. So now I can do this: kilogram to the N, meter to the M. That doesn't look right. How about to the P? And then second to the cube. So in that, you look at these two, and that's going to be 0. So for the P, I'm going to see 1 equal 1 minus 2, okay, 1 minus 2 plus 3. Okay, so that'd be what? 4 minus 2, or equal to 2. So that gives me 2. And then second would be -1. So it'd be meter squared over second. So I sort of goofed up here somewhere. This is sometimes put a big question mark. I was getting ready to goof up. I'm not sure I did quite yet, but one of the things I guess I did that I went from here to here, and that's when it sort of stumped me. So this is actually a more effective way of doing it anyway. So meter squared over second. Now let's go back and see, is that what? Yeah, so there you go right here, meter squared over a second. What does he do? He basically Newton meter. He goes through, well, he also, okay, he puts it in. That's weird. I guess you can do that if you wanted to. That's really weird. Joules per kilogram per second. Okay, that makes my brain hurt right there, why you would want to do it that way. But there obviously is a reason. So, and I'll let you finish the rest of that. So So all you do is just divide those two out, make sure you got the right units, and put it back into the system there. I don't want to do it because I don't want to. Oh, that's not fair. He should have made you do the units. So he's like, he did the units for you. What happens if what's part B? Express the answer in feet, foot, pounds, second units. Expression in 3 significant digits. Too tired to do that. Don't want to do that. Of course, you could just take that and convert it to that. All right. So if I go back here, well, I guess at this point, I probably should just let you go do these things. Then maybe come questions on Friday or something. So, is there any questions up until this point? Because chapter 2 is so significantly different. Here's what we'll do. If you come on Friday and you don't have any questions, I'll just go in chapter 2 and just start there. And give you the weekend, generate questions, what you want, and we can answer those next week or something. So, how about that? Is that a good idea? But I can give you let me just give you the layout of the whole thing. I mean, here's the whole course in a nutshell. So the first thing we do, I guess this is considered chapter 1, is like we focus on density, specific weight, specific gravity, viscosity, kinematic viscosity. I'll get used to that. I'll try to get used to that. And so these are kind of properties of fluids, and a little bit of the behavior of what shear stress does. Kind of like that. We look a little bit at that. Chapter 2, we start looking at fluid statics. And that's essentially like, I want to build a spillway to block and make a lake. I'm going to do like this, and it's a big rock on the ground, so there's a hydrostatic pressure on it. So what you find out is if you jump in water and start swimming down, the pressure gets greater and greater and greater the deeper you go. That's why if you get submarines down there, they're made like circles or tubes, because it'd be really a bad idea to make a submarine like that, because then under huge pressure, that shape would become more like this, because it would be just essentially the pressure would push it to the point it would pop the beams and drown. So the deeper you go, the higher the pressure. It turns out it's a linear relationship. So you'll see a hydrostatic pressure. So guess what? It becomes a statics problem. Here's your statics problem. Your static problem looks like this. You got a force here. You got weight of this thing. You got this. Is the spillway built such that it'll tip backwards, or start sliding, or just sit there dead still? So from that, you can judge what do you need to produce here. This shape needs to be in order to hold the water back. You get other weird things too, like you can take a cup of water and you can blow up a 55-gallon wine barrel to say, and this is a common thing. So you take a wine barrel like this. This is an awful drawing. Let me try to make it a little bit better. Take a wine barrel, oak barrel, kind of like this. Usually it has these metal straps around it to hold it. Bad looking thing. But you put a tube right there, and you make sure this tube is sealed around the edge. So if you pressurized it, it won't start leaking. But you make this thing so it's really a thin tube, something very, very thin. You take a glass of water, you fill up the barrel to about right here, and then you take a glass of water and you fill it up. As you fill that glass of water up, you find whatever the height is, the pressure, you'll find the pressure is equal to gamma times the height of the water above it. If you take a thin enough tube, fill it with water, you can take that pressure and shoot it really high in that barrel to the point where it'll pop those metal rings. And you can see some people who have done that. So it has really weird implications. There are all sorts of really weird and strange things that happen. And then and what you find out is, it's a lot of force. When you're starting to hold back water, you'll find a lot of force. You'll find some other things too, for example, let's say you want to be able to take a gate that you want, let me redraw it. Let me go down here and redraw it. Take a big concrete block and say you want to be able, at the end, you want to be able to hold this back so that water can flow through. So this is full of water. This force becomes very, very large. So how do you manage this so you can control water flow? If you go to the spillway, you'll see the gates are all made like this. They're all made in a circle. The reason they're made in a circle is because the force, the pressure, looks kind of like this. But these vectors are going right through this center. If this is a circular section, they're going right through that center. Meaning all you've got to do is open that, and if you open it, the water will flow underneath. That's why you can you go down there. Sometimes they've opened it a little bit. It can hold back tons of water. The water doesn't push it against the bearing so that it can't open. There are many times you could set it against something, and then once it sets, it's so much force you can't open it again. It just embeds itself in there. You can look back in history and find how people have made this mistake. Just not necessarily a mistake. People just didn't know that well. And, you'll find all sorts of things like that. And then it just goes on from there. So you know what I'll do? I just got my ride just showed up. So I think I may pick up and next time and tell you what the rest of the course is. And then we'll just start working in chapter 2 and just start doing problems. Chapter 2 can become problematic, but not terribly problematic. And we'll just go from there. So work some of those between now and next time. And then if you can't get them, don't fret. Just, work them over the weekend. I'll answer questions next time or next week. But in the meantime, I'm going to start spattering chapter 2 through there.